Alright, in this video I'm going to talk about electric fields. So we just learned that electric force is a field force. It's a force that is exerted in a region of space around a charge exerted on another charge. So we're actually able to quantify the magnitude of the electric field by relating to the force and the charge that's in that field. So an electric field is calculated by saying that E, which is the electric field, is equal to force per unit charge. And this is the charge that is in the field, right? That's being created by another object. So, for example, if I had a proton right here, and then over here, some distance away, I have an electron, right? And let's say there are 20 newtons of force acting on that electron as a result of the proton. I could actually figure out the magnitude of the electric field being experienced by this electron at this position. And I would just do that by using this equation. So I would take the force as 20 newtons, and the charge that is in the field is an electron, so it's 1.6 times 10 to the negative 19th. And I could get the electric field at that position. And so let's just do that. 20 divided by 1.6 second e to the negative 19th, which is E equal to 1.25 times 10 to the 20th. And the unit for that is actually newtons over coulombs. That's what we use for an electric field. Alright, so notice that I didn't put a minus or a plus sign in here because there is a convention for electric field lines. Electric field lines are vectors, and they point towards the negative or away from the positive. So electric field lines point towards the negative and away from positive. So the electric field as a result of this positive would be pointing in this direction. Okay, so now we can figure out both magnitude and direction. Now let's think of electric field in a different way. Let's say that this electron was not there. That does not mean that the field does not exist, right? So you've got a charged object, and around the charged object there is a region of space where a force could be exerted if a charge were to come into it. So there needs to be a way to calculate the electric field even if there is no charge present within that field. So how we do that is by using Coulomb's law. So remember that E is equal to F over Q. Now remember, this right here is the electric force. So if I plugged in Coulomb's law there, I would get K, and then I have Q1, Q2. Let's say this is Qi, the charge that's in the field, and let's call this Qm, the charge that's making the field, all over R squared. And then I would divide that by Q. Now, which Q is that? Remember, when we look at our problem here, that the Q, this is the Q that is in the field, not the one that is making the field. So underneath, this would be Qi, and we would get our Qi's to cancel. So now we have an equation for an electric field without there actually being a charge in it. It's relative to the charge that is making the field. So let's say again we had that same proton here, and I'm at some position, let's say 0.05 meters away. The question is, what is the strength and magnitude of the electric field at that position? Well, let's figure out the direction. If we're here at this position, we know that electric fields point away. So it would be pointing away from the positive. Now let's figure out the magnitude of this at this position. So we just say E is equal to K, which is 9 times 10 to the 9th. And then Q, which is, it's a proton, so 1.6 times 10 to the negative 19th, all over R squared. So let's plug it in. 9e to the 9th times 1.6 to the negative 19th divided by the distance. And so at that position, I have a electric field that's equal to 5.76 times 10 to the negative 7th. Remember, that's newtons per coulombs. All right, so what we have here is we have two different ways of calculating electric field. One is a scenario in which we have a charge in a field and there's a force being exerted upon it. So that is this case, and remember that this Q is the charge that is in the field, or the charge that has the force acting upon it. Then we have a second example where now we have a charge and it's making a field even though there's no charge present for a force to act on it, and we can solve using KQ over R squared. Now, just so you're aware of this, if you look in your reference tables under the equations for electric field, you'll see both of those equations written right here. However, it does not distinguish what the Q's are. It does not say one is the Q in the field or one is the Q making the field. So you got to make sure that you know the difference between this equation for electric field and this equation.